Our next speaker is Hubert Shum from Institute of Perception, Action and Behavior, School of Informatics, University of Edinburgh, where he is a PhD student, and his research interests are computer animation, human motion synthesis, and machine learning.
Good afternoon, everybody. I'm Hubert, and thank you for the introduction. Today I'm going to present my paper, which is titled Interaction Patch for Multi-Character Animation. The objective of this research is to generate multi-character interaction. Before I start the presentation, let me show you one of our experimental results. So here, the green character is interacting with a lot of blue characters, while the blue characters interact with other blue characters while they fall into each other. So this is a very, very difficult problem because you need to plan the motion for all of them. One potential approach to solve this problem is to apply cow simulation techniques. Well, for cow simulation, you can plan the motion of multiple characters for a given environment. But the problem is that you cannot handle dense interaction with cow simulation techniques. So here, dense interaction means the interaction with context with close interaction. And for example, in 2007, Shiraish et al. Present a paper using optimization techniques to generate a lot of characters walking in a given environment. However, the only interaction between the characters are mainly avoiding each other. Similarly, in 2008, Kwong et al. Present a paper that simulates a lot of characters walking in a town. Well, again, the interaction between the characters are mostly collision avoidance. And in 2007, Li et al. Present motion patches. The interactions are basically between the character and the environment, rather than between the characters, because the environment is static, is considered to be more easy. Another potential approach to solve this problem is to use interaction simulation, which simulates the interaction between the two characters. The problem is that it cannot handle many-to-many interactions. For example, Jordan presented a paper in 2007 to simulate a person when he is being pushed or being kicked. And Park et al. Presented a paper in 2004 to use Higamato model to generate two persons playing taekwondo. In 2006, Lee presented a paper to generate two avatars playing boxing by using reinforcement learning. For some of them, the system is fast enough such that you can put a lot of avatars, a lot of characters into the scenes. But overall, this kind of interaction between the characters are one-to-one. So basically, the character has a fixed opponent, and he always interacts with one opponent at a time only. So basically, it's very difficult to simulate dense interaction among multiple characters. If you use the cow simulation approach, it's very difficult for you to generate realistic dense interactions. If you use the interaction simulator approach, it's not trivial how you generate many-to-many interaction. In this paper, I'm going to present an approach that combines the benefits of the two algorithms. The overview of our system is like this. So we first capture the motion of a single person. And then we simulate the interaction between two characters. We save this kind of interaction into a data structure called interaction patches. And then during one time, we combine this kind of interaction patches in order to generate a large scenes in which a lot of characters interacting with each other. The captured motion are automatically segmented into actions in our system. And actions are the minimal units of movement. The actions are annotated. For example, in the fighting database, we have punch actions, we have kick actions, we have avoid actions, and we have falling down action when a person is being punched. Now we have some actions. We need to organize the action for the two characters. such that they are interacting with each other. We asked the animator to design a pattern list which defines the way the two characters interact. The pattern list basically lists the required type of action to be performed by each of the two characters. For example, here, I show you a pattern list. In this pattern list is a typical pattern for fighting. So here, character 1 first punch his opponent, and then his opponent, character 2, avoid the punch, counterattack with a kick, and character 1 avoid the kick. Now we have a pattern list. The problem is that for each action type we indicate in the pattern list, there might be a lot of instances of action that could fit in. For example, for a punch, you could have a straight punch, a hook punch, or even an uppercut. So basically, now you have a pattern list. You can generate a lot of series of actions that could fit in this pattern list. Therefore, we apply the game tree expansion approach to find out all these combinations. For example, here, we will expand a game tree with the first level to be the punch. We first list all the possible punch here, and we try to see what will happen if character 1 do a punch like this one, what character 2 will do for the avoid, and what character 2 will do later on for the counterattack of kick, and what will happen later on if character 1 to avoid the kick. So now we have an expanded game tree. We wish to convert game tree into what we call interaction patch. Basically here, in this game tree, every path from the root node to every leaf node form a series of interaction between the two characters. So basically, we can convert the game tree into interaction patch like this. Consider the path I highlight here. We can convert the path into a timeline between the two characters. So here, this is the time, and this is character 1 actions and character 2 actions. So character 1 first punch, character 2 avoid, and kick, and then character 1 avoid again. So you can see that because the actions themselves are continuous and the duration are different. So overall, the two characters act at the same time and interact with each other. Well, because for game tree, you can generate a lot of paths. It means that you have a lot of series of interaction between the two characters. So it's necessary for you to define something to evaluate the quality of interaction. The problem is that, unfortunately, it's very difficult to define a general rule for all possible types of interactions because there are really a lot of types of interactions. By our experience, we find that there are 3 types of criteria which always exist in a lot of types of interactions. The first one is the contact criterion. So, for example, like this figure here, the green character is kicking a blue character. So we actually wish the kicking position, the fit here, to be as close to the head of the opponent as possible, because there has to be a contact here. In this sense, this situation is supposed to be better, and this one is supposed to be not as good. The second criterion is the distance and the orientation. So for some motion like this one, in which the green avatar is avoiding the punch of the blue avatars. So green avatar is supposed to face the opponents because he wishes to keep track on the opponent. In this sense, this one is better, while this one is not quite natural, because when you avoid, you don't look into some other direction. By evaluating the orientation criteria, we find this one to be better because the green opponents always keep the orientation fixed to the opponent throughout the action. The final criterion is the timing. In this situation, the green character is actually blocking the kick of the blue characters. So you can imagine that the time the green character waves their arm and the time the blue character kick should be relatively close to each other. So by evaluating a timing criterion, we could find that this one is good, but this one is bad because the green character doesn't waste the hand in time. By evaluating all the interaction patches, we can find out the good instance of them. So here, I show you 4 examples of interaction patches. In the first 2, they are relatively simple. They are punch and fall and kick and fall only. In the lower 2 examples, they are relatively more complicated. There are 4 actions for the pattern list here. So you can see the green effort need to avoid and counterattack. So now we know how to generate the intention patches. So the intention patch is actually a short duration of intention between two characters. What we need to do is to combine these kind of intention patches to generate a large scenes in which a lot of characters fighting or interacting with each other. We propose two techniques to combine intention patches, the temporal concatenation techniques and the spatial concatenation techniques. First, I'm going to talk about temporal concatenations. Remember that the interaction patch only defines the short duration of interaction. So what will happen if we wish to have a longer duration? The objective of temporal concatenation is to generate longer interaction by combining shorter ones. So for example, here, we have two interaction patches. In the first patch, character 1 interacts with character 2. In the second one, character 1 interacts with character 3. Suppose character 1, the punch motion performed by character 1 here can be continued to perform the dodge motion here. We can actually combine the two patches like this, such that character 1 first interacts with character 2 and then continue to do some actions, the dodge here, to interact with character 3. Of course, we need to make sure that when we combine the two patches, character 2 does not collide with character 3. Another example is shown here. So suppose we have two patches. In both of them, character 1 interacts with character 2. We can combine the two patches like this one, such that both of them continue to interact with each other. An example of temporal concatenation is shown here. In the left-hand side, we have two interaction patches. In the first patch, the character kicked his opponent. In the second patch, he punched. So we can actually combine the two patches such that the green character first kick and then punch. Then I'm going to talk about the spatial concatenation. As you remember, the interaction patch only defines the interaction for two characters only. So what will happen if we wish to have many-to-many interactions? The objective of spatial concatenation is to generate interaction for many characters by combining interaction patches. Here, again, we have two interaction patches. Character 1 interacts with character 2 here, 1 with 3 here. Suppose the punching action we used here for the first character is exactly the same punching action we used for the character 1 in this patch. We can actually overlap the two patches like this. So as a result, character 1 first performed the avoid motion, which interacts with character 2 with the kick here, and then character 1 performed the punch action, which interacts concurrently with character 2 and character 3 at the same time. And finally, character 1 performed the kick and interact with character 3. Another example is shown here. Suppose the punch and the kick action is exactly the same as the punch and kick action here. We can actually overlap the whole patch here, like this. Then, when character 1 is performing this punch and kick, it concurrently interacts with two characters at the same time. Again, I show you an example here. On the left-hand side, we have two interaction patches. For the first patch, the green character kicks the opponent with the left leg, second one with the right leg, and finally we can generate a scenes in which green character kicks both characters at the same time. By this way, we can generate many-to-many interaction. Now we know how to do concatenation. We can actually repeatedly combine this kind of interaction patches to generate scenes in which a lot of characters interact with each other. One strategy to organize this final animation is to assume that there is a main character in the scenes, which is character 1 shown here in the timeline, who interacts with a lot of background characters, which are character 2 to character 6 here. So for example, here, character 1 first interacts with the red character, character 2, and interact with character 3. Also, character 3, the background character, can interact with character 4, another background character, when they fall into each other. and then character 1 continue to interact with character 5 and character 6. Okay. Another strategy to generate these scenes is to assume all the characters to be equally important. So here, character 1 first interact with character 2, and then both of them continue to interact with other characters. And of course, we can combine these two strategies to generate a wider variety of animations. And when we plan the motion here for the characters, we first plan the interaction first, and then we plan the motion for them to run into the scenes and go out of the scenes. Now I wish to visualize the interaction patch we used in the animation. So you can see that the circle below the two characters indicate that they are under the same interaction patches. So the green character interact with a lot of blue characters, and blue characters fall onto other blue characters by interaction patches as well. So now I'm going to show you some experimental results here. The first one I'm going to show is the American football. So here, the orange character is supposed to run into the goal line and avoiding those tackling defenders. The animator can give some optional commands to control the movement of the orange character, as shown in the arrows on the floor. Interaction patch we use in this example is mainly some running motion while other characters jump onto it, but this guy avoided the catch. Another example I'm going to show is a continuous fighting between two characters. You can see that these two characters continues to interact. This is done by repeatedly doing the temporal concatenation for the two characters. Here I show you an example in which a mouse runs into a cloud, and this character avoid the mouse and bump into each other. This mouse, we have interaction between the mouse and the character, and we have interaction patch between character and character when they jump into each other as well. So in this example, there are lots of characters moving luggage. They help each other to move luggage by passing the luggage one to another. So this is very special because this is a cooperative interactions. The interaction patch we use here is like one character first receive a luggage, transport it a little bit, and then give it to another characters. In this example, we try to create a user control interface such that the animator can generate the scenes. So as you can see here, the animator gives some high-level commands such as punch, kick, or avoid, and then the main character in the scenes will do the action accordingly. And then the system plans the whole scenes by applying the interaction patches. So you can see that the green character actually do the same actions, but now we have a lot of background character for him to hit. And you can see the background character fall into each other as well. Okay, finally, we generate scenes in which there are hundreds of characters falling onto each other. So basically, we use an interaction patch of one character falling onto another characters. And yeah, and the animator can provide a bitmap which is shown on the floor, as the letter you see. And only characters standing on that letters will fall. So, well, this is the demo with 500 characters as far as I remember. Beautiful, is it? So let me discuss a bit on our system. When I listened to previous talk, I agree that the simple algorithm is actually very important. So we try to use a small number of interaction patches such that we are more easier to maintain the quality of the interaction between the characters. And also, you just use less memory. So a feature of our system is that we can allow the user to design their own pattern list. Well, this is actually very important because according to our experience, the animator, actually they have a lot of things in their mind. They don't wish to be controlled by dynamics too much. So we allow them to design their own pattern list which gives them a large degree of freedom. But one drawback here is that because we need to design the pattern list, which is based on the annotation of the actions, it's very difficult for us to do some annotation for abstract and aimless action, and hence to design the patterns of interaction. And well, this question I have been asked for a lot of times, say, Hubert, is this algorithm, can it be used in games? So, well, the answer is not yet. There are two reasons for that one. First one is the controllability. Now we are actually giving a high-level degree of control to the characters. So we just tell him to punch, tell him to kick. But for games, we need to give very detailed control, such as move forward for 10 cm, move backwards for 10 cm, well, in which the character may not be able to find the appropriate interaction patches to conduct this kind of actions. So the solution probably is that we either increase the number of interaction patches, but this is not quite good because it increases the memory required. And another approach is that we can blend the interaction patch to dynamically generate some new ones. And another problem is the scenes organization strategy. Remember I said we plan the interaction first and then plan the movement towards the scenes and go out to the scenes later. So, well, this is not quite compatible to the games, but we can change it to some other controller for the characters. As a conclusion, we generate a kind of character interacting with one another. We first compute the interaction of two characters, and we save them into a data structure called interaction patches. And then finally, during one time, we concatenate these interaction patches to generate some last scenes. I would like to thank Professor Morishima-sensei. He helped us a lot during the whole implementation and during the whole development. And this project is funded by different funding bodies as shown here. Well, I'll just skip that. Thanks a lot.
If you have any questions, please step up to the microphone. And in the meantime, let me ask very interesting animations.
Thank you.
So are we going to see Greco-Roman wrestling next?
Yeah. Actually, wrestling is a very good example, but this is actually very difficult as well because there are lots of continuous contact. You can see that in this example here, I show the contact are basically momentary. So you punch, and the force is transferred, and this guy fall away. But for wrestling, you always hold the opponent. But our research group is actually doing some kind of topology for wrestling to maintain the contact with a good topology. So we can combine this kind of techniques with this system to generate interaction patch with contacts like wrestling, and then we can generate wrestling situation like this one.
In fact, even in this case, when you are doing spatial overlaps, when the character A was kicking with both feet so that it could hit character B and C at the same time.
Yeah.
And that wouldn't be evident if you're just looking at one interaction patch and the other interaction patch, right? So if there was a single foot kick and you did the spatial combination,
well,
then
sorry.
the third character would fall without having been kicked.
This is actually not like this because for each interaction patch, we assure that the interaction between the two characters are valid by the criteria like contact or something. So say, for example, if we have a kick and falling interaction patch, if we have a lot of them, all of them should be a valid kick and valid falling. The problem is that if the kick is not a strict kick, then probably the two character needs all standing at the same point because they can only be able to be kicked there. So by this way, we cannot concatenate them because they overlap. Okay. But for example, if this is a side kick, then actually there are multiple points of contact. Then we can place multiple characters by concatenate them.
Very good. There was a... Go ahead.
Okay. Good afternoon. My name is Nicholas Mario Wardana for Nanyang Technological University. I'd like to ask about the spatial concatenation. And in this section, you showed an example about what do you call it? A split kick that has two contact points.
Oh, double kick, you can say it.
Sorry?
You can say double kick.
Oh, okay. I'm not familiar with martial art. So, can you apply this method to concatenate simpler movement, like simple punch like this, which has only one contact point?
Yeah.
If you can, how do you determine the orientation of the main character? Okay, thank you.
Okay. I think the first question is somewhat similar to what you asked. So if you only have one point of contact, then you can still generate a lot of interaction patches, but probably you cannot concatenate them because all the characters are standing somewhat in the same position because they wish to be punched. So in that sense, when I try to concatenate them, they overlap. And then I find that it's not possible to do so. And then I just don't concatenate them. For a second question, sorry. For a second question about orientation, because, as I said, I plan the interaction of all the characters first. So I put the opponents in the correct orientation at what they are supposed to be. So if a punch is like this, and as stated in the interaction patch, they are supposed to be there in order for me to punch, then I place the opponent there. And then I plan backwards to see how these opponents should arrive into the scenes such that he will be there at that spot at the correct timing. So this is how I plan the whole scenes. Thank you.
No other question? All right, let's thank Hubert one more time.